Yeah. Oh, yeah, he does. That one actually. Sorry, I got it. Okay, got a few pages of lecture notes here actually, and then we'll spend the rest of the period working through some practice problems on inverse Fourier transforms using this handout. It's got, I put the same table number as the table that's in the textbook, but it's got a few more transforms and properties than the table in the textbook. And the other thing is he doesn't have very many problems on inverse Fourier transforms. Not quite sure why. So if you go to the lecture link today, it says S14, S15, S22. That's out of, just click on this link and there, it's from, although they don't say S, the S is just from supplemental problems. So 14, 15, and then 22 is in this file. And I'll be giving some additional homework out of this file for the next couple of lectures. So in just quickly, so we can get to some problems. Fourier transform properties. Of course, the time shift is probably one of the most important Fourier transforms properties, that if you've got one signal that is a time shifted version of another, then their transforms are related. the transform of the time shifted signal is e to the minus j omega t0 times the transform of the unshifted function. And t0 is the time shift. And this is kind of very much like Laplace transforms, where we had e to the minus s t0 for the property in the Laplace transform domain. So a very simple example, x of t is u of t minus t0. So we can start with a simpler function, and I'll work through this kind of in more detail. Now, the Laplace transform of u of t is just 1 over s. The Fourier transform is a little more complicated. It's got a 1 over s type term, but it's also got an impulse. So there's the 1 over s term plus this impulse. So this is the Laplace transform of the unit step. Now, since x of t would be w of t minus t0, substitute t minus t0 in here, right? U of t minus t0, then x of omega is e to the minus j omega t0 times w of omega, or x of omega times e to the minus j omega t0 pi delta omega plus 1 over j omega. Now, if I multiply this through, what do I get when I multiply e to the minus j omega t0 times delta of omega? It's a little bit odd because we've been primarily working with impulses in the time domain. This is an impulse in the frequency domain. But the multiplication property still applies, but it's where is the impulse located in the frequency domain? It's at omega equal to 0. It's not a shifted impulse. So I evaluate the time function that's multiplying it at omega equals 0. So e to the 0 is 1. So this reduces to pi delta omega plus, now I can't do anything with the other term. So that would be the Fourier transform of the shifted unit step. Some other ones I'll just state. Time scaling, x of a t. So an a could be positive or negative. It's 1 over the absolute value of a. X of omega over a is the corresponding Fourier transform. Time scaling is not something you do in practice, but in some of these mathematical problems in relating one signal to another, it pops up. Yes.
Where did the second e to the minus j omega t go?
Here?
Yes.
So using the multiplication property of the impulse.
Oh, yes, understood.
So I evaluate this at omega equal to 0. E to the 0 is 1.
And that w, is it omega or
It is omega.
a dummy variable?
It's our frequency variable. It's like S was our complex frequency domain variable. By convention, tradition, we use omega as our Fourier transform variable. It represents frequency in radians per second. Okay, just like we do in, for our cosines and sines. It's that same frequency variable. Because cosine omega 0 t transforms into well, delta omega minus omega 0, and then there's a,
So where does omega t come from? Omega t is equal to u of t, the step function.
oh, sorry, this is not an omega, this is a w, a time domain function.
But you use something. Yeah.
Sorry, this is a w. So I was, let me change this
Q.
to y, okay. Which means, so what I was trying to define was a simpler function, simpler than the function we were given, and then relate the transforms. So here I would have x of omega is just e to the minus j omega t0 times y of omega. Can't tell the difference between my w's and my omegas. Sorry. I couldn't tell the difference either. You have to know by context, I guess. Is that okay? Anything else? Okay. This is probably the most fundamental property of communication systems. It is, here I'll show it multiplying by a complex exponential. What it does is it shifts the transform in the frequency domain. Okay. Now this is multiplying by a complex exponential, writing cosine as, using Euler's formula, as 1/2 e to the plus j omega 0 t plus 1/2 e to the minus j omega 0 t gives you this. And this is fundamental to how all modern wireless communications methods work. So for example, and AM radio isn't much different than this. Let's say take a message coming in off of a microphone. That's a low frequency message. If it's in a voice, it's typically frequencies between 0 and like 4 kilohertz. If it's music, it goes up to maybe 15, 16 kilohertz. To transmit it wirelessly, efficiently, we have to translate it up to a much higher frequency. In order to do that, you just have to multiply it by a cosine omega 0 t. So if x of omega, for example, looks like this, then the Fourier transform of cosine omega 0 t x of t. So this is the Fourier transform of x of t. What we get by doing this, just multiplication by a cosine in the time domain, it shifts the spectrum. This is a shift to the right, and there's a multiplication factor by 1/2 to omega 0. And again, we have to have this symmetry in the frequency domain in order to keep it a real signal. So if this were A, this would be actually A over 2. But this would translate it up to, let's say for AM radio goes from 660 kilohertz up to 14, 16 something. I forget what the range of AM radio, 16. You guys listen to AM radio all the time, I'm sure, right? So 16 or FM. So on the AM radio dial, those numbers are in kilohertz. Okay, so it's like 660 kilohertz to 1700 kilohertz. That's 1.7 megahertz. What are the numbers on your FM dial? What's a typical number there? Can't hear you. 80, yeah. 88.2, what's WEV? 96 point something? I don't know, it's 96.8. Those are megahertz. Okay, so the FM frequencies are like 100 times the AM frequencies. But and those are the different carrier frequencies that are used by what are called the carrier frequencies. But at least for AM, it's pretty much just this, multiplied by cosine to translate the signal. FM is a little bit more complicated, but AM is not much different than this. And there's two reasons they modulate. One is so that they can transmit it efficiently via antenna, you can receive it efficiently. The other reason they modulate is for what's called multiplexing, so that you can have all these different radio stations transmitting simultaneously. They use different carrier frequencies, so another, if you have another one that looks like this, it would be translated to a different carrier frequency, a different number on your radio, right? So when we're using our radio receiver and tuning to a particular station, we want to listen to this one, it's just passing through this one and filtering out the others. Or then if we want to listen to the next one, we just turn our tuning knob, passes through the one we're interested in and filters out the other. FM works similarly. They use different carrier frequencies in FM to get this called frequency domain multiplexing, or FDM, so that you can have all these different stations. But it's really, again, for AM, not much more complicated than just multiplying by a cosine to get that modulation. To actually demodulate, one way is multiply by a cosine again. Because if we multiply by a cosine again, so we take this, multiplying by a cosine, multiply this by a cosine, would shift it to the right by omega 0. So that means this thing would be here. This thing would be up at 2 omega 0. And then add to that, the thing shifted to the left. So this would now be here added to this, so actually twice as high. And this would be down at minus 2 omega 0. Low pass filter this, and we've got back our original signal. So it's a little bit more complicated than that, but not much more. But that is fundamental to cell phones, high def television, AM, FM radio, satellite communications, Wi-Fi, all use some form of modulation. And you double E's, get a whole course on that next year, don't they, Franny? So got that to look forward to. I'm smiling under here, so differentiation and integration. DXDT transforms as J omega X of omega. It's like in the Laplace domain, it was S times X of S. And then we had a term related to the initial value of the function, but you don't have that with beta Fourier transforms. The integral, like what you might get with an op-amp integrator, 1 over J omega X of omega. That's, again, kind of corresponds to division by S, but then there's another impulse term that appears if there's any average value in X of 0. If X of omega evaluated at omega equal to 0 is non-zero, you pick up that last term. And then the final property is convolution and multiplication. Of course, this is the most important property with regard to circuit analysis, convolution or systems analysis. Convolution in the time domain becomes multiplication in the frequency domain. Multiplication is a lot easier than convolution. Multiplication in the time domain is convolution in the frequency domain. Here we're involving these two functions as functions of omega. There's this 1/2 pi factor that appears because, again, the Fourier transform integral or operation and the inverse Fourier transform integral or operation are very similar. They're almost identical integrals, except for a minus sign and a 1/2 pi factor. Okay, so there's another property called duality. It's on the table I'm not going to mention. But because those transforms are so similar, you can actually use as your time domain function a function in the right-hand column where I've got the frequency domain one's listed, and then the inverse transform is actually in the left hand. Okay, we'll work through a bunch of examples. I need to just briefly mention Parsifal's theorem. We had Parsifal's theorem when we talked about Fourier series. It allowed us to calculate power using from the Fourier series coefficients. The energy of a signal is this is the definition of the energy of a signal, just the integral of the function squared. I put the absolute value in there in case it's a complex function, but if it's a real function, you don't need the absolute values. Simple. Well, in the frequency domain, 1/2 pi integral from -infinity to infinity of x of omega squared d omega. And for a real signal, you have this symmetry in the transform domain. So x of minus omega, absolute value, is equal to the absolute value of the conjugate. But the absolute value of the conjugate is the same as the absolute value of the original function. So x of omega squared is an even function. So instead of integrating from -infinity to infinity, you can just integrate from 0 to infinity of x of omega squared and double that result. And so the 1/2 becomes just 1/2 pi becomes 1/pi. And finally, the energy in omega 1 to omega 2 band is from this, we can just integrate over the positive frequencies. Normally, when we talk about the energy with from 10 kilohertz to 15 kilohertz, again, that would include the energy and the corresponding negative frequencies, because both those negative and positive frequencies are necessary to make up the real signal. But you can avoid the negative frequencies by using this integral, which already automatically includes the energy from both the positive and negative frequencies. Okay, so let's look at some inverse transforms and just a bunch of examples. I'm going to put some up here, give you a few minutes to work on them. See if you can find I think pretty sure the first two are almost exactly in the table. You might have to play a little bit of an algebraic trick. That third one, you're going to want to use partial fraction expansion on. So give that a try. And then we'll talk about, give you every 10 minutes to work on these. And we'll go over them. We change this one to j omega plus 1, j omega plus 2. I'll talk, since that one's got a minus sign in it. Talk about what that means. Did you find this one? What pair is it in the table? 7A. Notice the restriction at the top of the table that A and all of these has to be greater than 0. So does it still fit 7A? It does fit 7B, right? Because you can write this as -5 over minus j omega plus 2, or -5 over 2 minus j omega, which is how it's written in 7B, isn't it? Yeah. So the g of t would be -5 e to the 2t u of minus t. Now, what does that look like? U of minus t is 0 for t positive, and it's 1 for t negative. Well, -5, so t equal to 0, this would actually be -5. But as t becomes more negative, this is a decaying exponential on this side of the axis, right? So it actually looks something like this. Now, if this were a Laplace transform, though, and it were 5 over s minus 2, where would the pole be? The denominator were s minus 2. What value of s would make that 0? S equal to 2, right? Where in the s plane is s equal to 2? The left half plane or the right half plane? It's in the right half plane. So if this were a Laplace transform, it would correspond to an increasing exponential times u of t. Now, in the Fourier transforms of like increasing exponentials don't exist. What we have with the Fourier transform are the negative time functions. Okay, with the Laplace transform, this would come back as 5 e to the 2t u of t, an increasing exponential in positive time. In Fourier transforms, though, we've given that up. Okay, these functions that would, if you had an s in here instead of j omega, the pole here is really, at omega equal j2. If you substitute an s here and it's in the right half plane, that actually means it comes back as a negative time function in the Fourier transform. And it's one of the reasons we don't use Fourier transforms to talk about stability of systems. Fourier transforms are more useful in communication systems. We now have this ability to talk about functions for negative t that we couldn't talk about with Laplace transforms. So just watch out for that. Did you find B in the table?
Yes.
Which one was it? 14? I think it's 14 and not 11. Why is it not 11? There's no j in here. A plus j omega squared, even if you multiply that out, it would be a squared plus 2j omega minus omega squared, which is much different than this. It is 14. It almost exactly matches, well, 14 is written like this. Well, it's got 2 squared plus omega squared. And then I have to get a 2 times 2 in the numerator.
6 times.
Well, I'm trying to match the pattern, right? So now this exactly matches 14. Right, where it's got 2a over a squared plus omega squared. Do you agree with that? Okay. So that means h of t would come back then as what, 3e to the minus 2t u of t. Nope, I'm sorry. It's absolute value of t, isn't it? So this actually includes, this would look like this. It includes positive and negative time. It's defined over all time. You can actually expand that. Let's do that. I could write this as is that right? It's going to give me 4, and then the inner terms are going to cancel. I have 2j omega minus 2j omega, and then j omega times minus j omega is omega squared. So I could write this like that, right? Let me write this like this. Don't really need to do that, but I can do a partial fraction expansion on this. So now you don't want to do a partial fraction expansion letting omega be the variable. Let j omega be your variable. Or if it helps, substitute s or x or f or whatever you want in for j omega. But now for the 2 minus j omega in the cover up method, I cover this up and let j omega equal 2, right? That's where this would go to 0. So I'm going to have minus 12 over 4 or minus 3. Okay. Cover this one up, I'm going to let j omega equal minus 2. So I have minus 12 over plus 4. Right? So that's also minus 3. Okay. Now, what do these match? Well, yes, 7a and 7b, right? If I messed this up somewhere, lost the minus sign. I don't know why I did that. Yeah, I just screwed up there. That minus sign is not supposed to be there, right? Where it came from. So now if I take the transform back of these, this is going to be 3e to the 2t u of minus t. And the second one is 3e to the minus 2t u of t. Did I get a different result? They look different, right? But this is 3e to the minus 2 absolute value of t, which means this segment is 3e to the minus 2t. Absolute value of positive t is t. But this side is 3 e to the absolute value of a negative t, that's a negative t. So that's plus 2t. I can view this as this segment times u of t plus this segment times u of minus t, which is what this is saying. Okay, so they are actually equivalent. Okay, any questions? They do a good job of losing everyone there. It's the goal, at least, once a lecture. Any questions? Okay, what are we going to do with C? That's not in the table, is it? Omega plus 1, J omega plus 2. Suggestions? Partial fractions. And again, if it helps, you could do a trick like this. If s plus 2, and then now don't forget to replace s with j omega when you get done, because we're doing Fourier transforms. And so the cover up here would be let s equal minus 1, so I've got 10 over 1. Let s equal minus 2, I've got 10 over minus 1. And then so alternatively, you can do it directly in terms of j omega. But you don't want to get caught up in letting omega be the variable. What does j omega have to be for this to be equal to 0? J omega has to be equal to minus 1, right? So again, when we cover this up, what we're going to do is let j omega be minus 1, and we get 10 over 1. Here we're going to let j omega be minus 2. So we let j omega be minus 2, so we'll have minus 2 plus 1 or minus 1. 10 over minus 1 is 10. So we get the same partial fraction expansion. All right, so now the way I had this written originally was like j omega minus 1 and j omega minus 2, which means they would both be u of minus t functions. But these poles are in the left half plane. Again, and they're not really poles of this function. J omega would have to actually be minus 1. But this would now be what? 10 e to the minus t u of t minus 10 e to the minus 2t u of t. Okay, we've got a few minutes. Give you a couple more. Give you a couple minutes to work on those two inverse Fourier transforms. Okay, so J omega plus 10. So partial fraction expansion. What'd you get over the J omega? -10. And over the other one? -10. Everyone get that? Any questions about that? Just simple cover up. What's this one? Is that in the table? Which one is it? 4? Is that the signum function? So what's it come back as? 5 signum? Yeah, a 1 over J omega is going to come back as a signum or a U of t. There is a factor of 1/2 in there. Isn't that in there?
Yeah.
And then this would be -10 e to the -10 t U of t. What do we do with B? Does that simplify? Doesn't? Plug in omega equal to 0. Anytime you got delta t times something or delta omega times something, you can immediately simplify it. Here is located at omega equal to 0. So this is 1 over J omega plus 1, J omega plus 2, delta omega. So I substitute omega equals 0 there, I get 1/2 delta omega. Now, is that in the table? Well, 2 pi delta omega is so what do I got to do? Multiply that by 1 over 4 pi to get back to 1/2. Did I do that right? I think so. So 2 pi delta omega, according to transform number 3, pair number 3 comes back as 1. So this becomes just 1 over 4 pi, just a constant. All right, good timing. See everyone on Friday.